Okay, good morning, everyone. This is the second lecture of the forward and inverse modeling course. And today we are going to move forward building on the flow simulator pressure solver that we have developed so far, and now go forward and do a saturation transport solver. So with that, I'd like to change my screen and go to whiteboard. Do you see my whiteboard?
Yes.
Okay, great. So let me just do some sort of work here on the pad to give you the right context of what is it that we are going to do with this transport simulator. We have already developed pressure solver. We started with a mass balance equation that for incompressible flow was written as D as phi ds alpha dt minus divergence of lambda alpha gradient P was Q alpha. So the first term is the saturation. This is the phase saturation, volume fraction of phase alpha. Lambda alpha is the phase mobility and permeability also involved. So K, Kr over viscosity, and Q is the source term. Okay. Now, imagine we have two-phase flow. I just want to make it simple so we can understand and do some analysis here. I have assumed also incompressible here. Incompressible flow and also rock. Porosity does not change over time as well. Now, I'd like to do something. I want to also write it for phase beta. Imagine I have two-phase system. So I have phi ds beta dt minus divergence lambda beta grad pressure is Q beta. Now I have another constraint that when I have porous rock and I have some sort of grains here, so these are solid part of my porous rock. These are the solid parts. I have phase alpha, which is part of this empty and void space. So it is in part of this empty space. And I have phase beta, which is, for example, let's say the yellow phase, and it fills the rest. So I'm just making some simplification. In the pore scale, it never would happen like that. So I just want to give you some perspective. So if you have a grid block, you have part of it, phase alpha, part of it, phase beta. So if you just average this whole thing out, you will get that I have some saturation for phase alpha, some saturation for phase beta. But the important thing is that both of them fill the entire void space. So the summation would be 1. That's the physical constraint that we have. Summation of saturations becomes 1. So if you have 20% gas, you would have 80% of the other fluid. If you have 40% of phase alpha, you would have 60% of the other fluid. So the summation would always end up to be 1. So there is no vacuum, there is no void space that would not be filled with anything. So we will write mass balance for all the phases that would add up to 1. So in this case, I have S alpha plus S beta is 1. I can in fact do something nice. I can actually replace this equation by using this formula and write whatever beta I have as 1 minus S alpha, right? Because S alpha plus S beta is 1. So that means S beta is 1 minus S alpha, right? That's very simple. Instead of solving for S alpha and S beta, I can solve for S alpha, and I know that S beta is 1 minus S alpha, right? Because the summation is 1. So what would I get at the end? I would get d dt, phi dt of S minus divergence lambda alpha grad p. This is S alpha. I can keep it alpha because I will have 1s is q alpha, and I have phi d dt of 1 minus S alpha minus divergence of lambda beta grad p will be q beta. That's my balance equation for phase alpha, phase beta. Here, where S beta is written as 1 minus S alpha because the summation is 1. Now I have one question for you. How many equations do I have here? Hida, you are the new student in the class. How many equations do you see here? Unmute yourself.
In terms of what?
How many equations do I have? How many are they?
It is simply 3 of them, but probably they're
exactly. They were 3, which were here. These are 3, 1, 2, 3. But we used the third one and combined it with the second one. We use this relationship to change S beta to be 1 minus S alpha. And so at the end, we have ended up with 2 equations. Yeah. So we have ended up with 2 equations. So that would be the first equation that would be written for phase alpha. And the other one is for phase beta, in which we have already used our constraint that the summation of the 2 phases is 1. We have already used this. So I have 2 equations. Okay, 2 equations. One for phase alpha, one for phase beta. And I have used the constraint already there. Okay, fine. How many unknowns do I have? How many unknowns? Not unknown, unknowns.
Knowns.
How many do I have?
Who?
Pierre, are you with us today?
Yes, I am.
Okay, unmute yourself. How many unknowns do we have in this? Asking you made Alex happy, so I'm glad that I asked you. So, yeah. How many unknowns do I have?
I'd say we don't know anything at the moment.
We don't know. It's an excellent answer, Pierre. So, look at this. We are developing a reservoir simulator, meaning that we are going to receive some input file anyhow from geologists, from petrophysicists, from everybody. We need to know lambda. We need to know the property of the fluid. Like we need to know permeability of the rock. We need to know porosity of the rock. So these are the parameters that we would receive as input in our simulator. These are the descriptions. And if we have wells, how are they doing? What do I need to know over time dynamically to describe the location of the phases and the pressure distribution in my system if it is two-phase flow system?
We also don't know the pressure, right?
Pressure is the main unknown here, of course. Pressure is one of the quantities that I need to solve for. And we solved for it in the previous lecture for flow problem. Now that I have two-phase flow, would knowing only pressure be enough? For two-phase flow, when I have two fluids, can I just describe the entire system only with knowing pressure? So I say, hey, you know what? You have let's say a reservoir in which you have two phases. Imagine you have oil and gas. Then at this node, you have pressure to be, I don't know, 50 bars. Would that be enough for you? And totally the fluids are traveling with 1 foot per day.
But you need to know the rock, like
no, rock is given. Look. These are the terms that input.
We know those.
We know those from input parameter. Without them, we cannot even solve for anything.
Okay.
We know the geometry of the reservoir. We know boundary condition. We know locations of the wells. But would only pressure and velocity be enough to know everything about this system? Look at this equation. What is the additional unknown that I have?
Saturation.
Saturation. I need to know for each location in my reservoir, what is the pressure, velocity, and how much of phase alpha do I have? How much of phase beta do I have, right?
Yep.
And I know the summation of the saturations is 1, so I need to know one of them. So S alpha is the other main unknown that I have. So I have two unknowns, S alpha and P. And I know that node S beta is 1 minus S alpha.
How could you know?
What?
The saturation?
Would be, no, I don't know. I need to solve the equations for it. I have two equations for two unknowns. When I solve these two equations, I can find pressure and saturation if all other terms are given to me. If boundary conditions are given to me, initial conditions are given to me, and all the physical properties and fluid and rock properties. If fluid and rock properties are given to me as well, I need to solve for saturation of phase alpha and pressure, and then I will be done.
Is it possible to determine it in a production well or not?
No. You need to know the entire distribution of pressure and saturation everywhere in the domain. Everywhere in the domain. Look at my previous slide that I had started the lecture with. Do you remember this slide? This is the saturation distribution after some time, right? This is the saturation distribution. You need to know the pressure distribution and velocity distribution everywhere in your reservoir, and the injected fluid, how would it go? Which is, where is it? How much of gas do you have? How much oil do you have? Or how much heat, hot water do you have? How, you need to have a transport property here to see what has happened after you have injected your new fluid in the system. Okay. Now, I want to be back to my whiteboard. Okay. Now I have two-phase flow system. And I know that For that, I have two unknowns, pressure and saturation, to solve for. Now, naturally, one would ask himself or herself, why wouldn't we just discretize these two equations together? We develop a finite element, a finite difference, finite volume method, like what we did, finite difference method and finite volume so far for the pressure. Why don't we just do the same thing now for the entire two-phase system, discretize them, develop a code, and solve for pressure and saturation together at the same time? Why wouldn't we just do this? Why shouldn't we just simply discretize them and find linear systems that would give me pressure and saturation for phase alpha in one linear system, by solving it, I would get pressure and saturation at the same time, fully coupled. We call this approach fully implicit approach. Or simultaneous, fully implicit, which is everybody is coupled together. Pressure and saturation both are coming from a fully coupled system. So you would solve and discretize all of them, equation 1 and equation 2, and would get for pressure and saturation a fully implicit system. Why do you think this would work or this would not work well? Do you have any idea about this? Someone please just share your view with us. Would you think first that Ewald, are you with us?
Yes.
So do you think this would be a feasible way to do the simulation?
Yeah, I'm not that familiar with linear algebra.
Yeah, but it's not about linear algebra. It's more about physical simulation, right? And I know that you don't know the answer. I want just to have what would you naturally think that, you know, I have a 1D reservoir. I will discretize it like this. I put my pressure and saturations in the centers. Then I would put my velocity at the interfaces. And I would start to discretize and solve this pressure and saturation fully coupled simultaneously together. Well, the answer is it would work, but it wouldn't be efficient. You would need preconditioner, you would need a lot of tuning, and at the end of the day, this is a lot more expensive than you would have done it otherwise. Why it is not the smart way to do this? The reason behind this is that the pressure and saturation are two different unknowns. They live in different worlds. Pressure is global. Pressure is global. If it is incompressible like this one, everywhere would be affected by pressure. Pressure is a stencil that needs a stencil that would extend the entire reservoir to chain together. If you change lambda in one place in the reservoir, pressure would be different in everywhere in the system. But saturation is the amount of fluid, and it will be injected through time, through the reservoir. Saturation is local. Saturation is like a wave that has a speed of travel in the system. You inject water in an oil reservoir, water over time would progress through the reservoir and would come. Imagine you have a kind of coming stream of water. Someone has just, you know, thrown some bucket of water on the earth, and then you are here. You have no idea of what's going on, except that you may you may feel the pressure is higher around you. And then poof, you get wet. Until you do not feel, the water droplets don't touch your face, you wouldn't notice there are water droplets on there. This is transport of something. But pressure is more global. Pressure, if you change the pressure of the room, you would feel it everywhere. If you start to increase the pressure, well, it would take time to get the full sense of it because it's compressible air we live in. But if you were in an incompressible, if compressibility was very small, then you would immediately, in an elliptic way, you would understand that change. So for that reason, reservoir simulators have come up with an approach which is called sequential approach. Sequential approach is that you better decouple them and solve for them step by step. So simulator people say that since pressure and saturation are different species, they are different species. So this means that they say, well, you know what? Pressure and saturation are different species. One is global, another is local. Therefore, let us develop a sequential simulation strategy instead of fully implicit. Especially here, we do not have capillarity, no capillary pressure. You're going to learn about it in future, and no compositional effects. There are some complex physics that would make the pressure and saturation look more similar than what we see here. We do not have capillary pressure, no compositional effects. So it is just a straightforward decision for us to develop sequential approach. When the capillary pressure and compositional effects are not there, the two unknowns, pressure and saturations, are just so different. They live in different worlds. One is elliptic, another is hyperbolic, that they don't really, it doesn't make too much of a sense to put them all into one system of equation and make a huge system of equation, irrespective of having it even complex and computationally expensive. It would also not be a wise thing to do. So for that, we do sequential approach. How do we do sequential approach? Let's develop the sequential strategy. I have phi ds alpha dt minus divergence lambda alpha grad p is q alpha. And then I have phi ddt 1 minus s alpha minus divergence lambda beta grad p equals q beta. I'd like to develop a sequential simulation strategy. What would I do is that I sum the two equations up. If I sum the two up, I get phi d dt s alpha plus 1 minus s alpha minus divergence lambda alpha plus beta grad p equals q alpha plus beta. S alpha and minus S alpha, they cancel. What's the time derivative of 1? What's the derivative of a constant value? 0. So then I would get rid of this term entirely. So I would simply delete this whole term and say this is 0. And so I will reach to this very nice equation that would say minus divergence lambda grad p equals q. Knowing that lambda here is simply lambda alpha plus lambda beta, and this Q is Q alpha plus Q beta. So by summing them up, my friends, by summing them up, I could get rid of saturation in an equation like this. I could get rid of saturation because I used the fact that the summation of saturation is 1 and change over time of 1 is 0. So if when I sum the two up, there is no existence of saturation. Fabulous. Because now I can solve this pressure equation without much information of saturation because there is no ddt of saturation anymore here. So I will replace this equation with one of them. So instead of solving equation 1 and equation 2, I wouldn't solve equation 2, I would solve equation 2 prime or equation 3, which is the summation of equation 1 and 2. So it's a linear combination of them. So I would actually solve equation number 3, this one, which is the pressure equation. I replace 2 with 3. And the good thing about 3 is that it's 1 plus 2. So it's actually coming from equation 1 plus equation 2, which has the beauty of not having any ddt of saturation in it. All others have ddt of saturation in them. This way, I could decouple them as much as possible. So how am I going to solve this system? Is that I am going to do this. I am going to first solve my pressure equation. So I'm going to solve this. Then I'm going to solve equation number 1, which is what? Which is phi ds alpha dt minus divergence lambda alpha grad p equals q. Okay, q alpha. I need to do some mathematics here. When I solve pressure as a step 1, as the real step 1, I need to, after that, find velocity total, which is minus lambda grad p. This is total velocity. Then what I am going to do is I'm going to replace lambda alpha with lambda alpha divided by the total lambda, which is lambda, times lambda, times lambda. So I'm going to replace this with lambda alpha over lambda times lambda. So let me put it here. I'm going to delete the lambda alpha. Instead, I'm going to write it lambda alpha divided by lambda times lambda. Now, what is minus lambda times grad p? Minus lambda times grad p. This is velocity. So I would actually write this equation in another form. I would write it as phi ds alpha over dt plus divergence of lambda alpha over total lambda u is q alpha. And this u is exactly the u that I have calculated up in here. And then I have a terminology. For lambda alpha divided by lambda, we call this fractional flow function. This is f alpha. We define it. F alpha is defined as lambda alpha over total lambda, which is lambda alpha divided by lambda alpha plus lambda beta. Fractional flow. We have in our lambdas permeability involved already. So our lambdas are k times kr over viscosity. But since k is constant for alpha or lambda total and lambda alpha, it will cancel each other out from numerator and denominator. So it's not precisely fractional flow. Fractional flow really does not have k in any term, even numerator or denominator. But since we have included them in the we have included this permeability in the numerator and denominator, then it would cancel. So you would get the same value. So please allow me now tidy up, write everything tidy into a new sheet of paper. My sequential strategy is this: sequential simulation for incompressible flow, no capillary, no composition. So how would I? No composition. So let me just make it a little bit, then write it a little bit. No capillary, no compositional effect. Compositional. How would I do that? First, solve for pressure. How? Minus divergence lambda grad P is Q. 2, compute velocity, total velocity, which is U is minus lambda grad P. Step 3 is update or solve for saturation alpha, which means phi ds alpha over dt plus divergence f alpha u is q alpha. The main unknown here is P, which is this gentleman here. The main unknown in the second stage is velocity, which is this lady here. And S alpha is the main unknown here, which is here. And we know that F alpha, which is fractional flow of phase alpha, depends heavily on the saturation. It's a function of saturation. But these functionalities are going to be given to you. With this way, we first do step 1, then we do step 2, then we do step 3. So we do step 1, then a step 2, and then a step 3. That's why we call it sequential simulation, step by step. In sequences, we solve for the both unknowns of pressure and saturation. Yeah. That's why it is sequential simulation. Now, we have already covered pressure and velocity in our first lecture. We already have developed a finite element or finite volume method solving for pressure and velocity. We put pressure at the cell centers, velocities at the interfaces, right? This lecture is about how to solve equation number 3. This lecture is if I know my velocity from my pressure solution part, if I know my porosity from my geological characterization and geophysical characterization, if I know my source terms, location of wells and their configurations, what would be my saturation change over time? How would saturation change over time? How would I, if I look into one grid block, first I have 100%, let's say, methane, and then over time, hydrogen is coming. Then I would change the composition. Instead of 100% methane, 0 hydrogen, over time it will be 80% methane, 20% hydrogen, 60% methane, 40% hydrogen, all the way to 100% hydrogen, 0 methane. That would be what you would see in these sort of simulations. I believe that you have seen it also in your previous lecture extensively. I'm trying to look for it and see, yes, I I have shown it to you before. Let me see if I can change my share screen. You should be able to see my other screen. Do you see my presentation screen here?
Yes.
See, the fluids are coming forward, backward. This is saturation of it. I need to see this time dependency, this dynamic invasion of phase beta to the reservoir filled with phase alpha. That's the saturation transport. This is the subject of what we are going to discuss in this lecture. Yeah. So let me go back to my whiteboard and exit this one. Okay, so that's the saturation. So now we know what the governing equations are and how are we going to solve them, right? So that's my governing equation. Okay. And I know that I know how to solve for pressure. I know how to solve for velocity from my lecture 1, and the homework of which I'm going to submit on Monday evening. And Hadi would grade them with human heart, knowing that there was a little bit of confusion. I'll try to become more human in grading. So having soft permeability, because I am also a porous body as well. Everybody is porous, so I try to increase my permeability and be softer, and elasticity coefficient a little bit smaller, so I'm softer than normal. Depends on what food I get, how do I feel. So it depends on how you submit your reports. Then my elasticity factor changes, my permeability, porosity changes. So it's just human. We all are flow in porous media at the end. Now with this transport part, this is the subject of the lecture of today and the practical of this week. We would like to know, how are we going to solve this equation? So that's the subject of the lecture today. How should I solve if I know the velocity from my pressure part? If I know my velocity, if I know my well configuration and I know my porosity, how would I solve this equation? And for that, to make it simple like flow, we will start with 1D system. For 1D, one-dimensional reservoirs, it would read phi ds or ds alpha, because I have one saturation unknown. I can write it s, but that's okay. Plus d dx of f alpha u is q alpha. By the way, sometimes we write u as ut, okay? Sometimes we write u as ut, which is total. This is total. They are all the same, okay? Sometimes we write it as u tot. Also, it is total velocity. So it's different indices. So just please don't get confused. One quick question. How about S beta? What would be the saturation of S beta if I know S alpha?
One minus.
Exactly. So I solve for saturation of alpha, and I know that as a post-processing step, if I want, I can also say that S beta is 1 minus S alpha, if I really want it. If I don't want it, I just would report S alpha. I know that the person who is looking at it would know that S beta should be the remainder to the 100%. So if I say gas is 50% here, the other person would know that's okay. The liquid is actually 50% as well. So how would I solve this problem? So I guess it's a time for a good break. So take a 15 minutes break. I'm going to stop sharing my screen. And okay, so we left at this point. We would like to solve this for 1D problem. Okay, so let's do a little bit of also arrangements for this to better understand this equation. Just for you to know, you know that in 1D incompressible flow, 1D incompressible flow, and one of you texted in the message that why would you assume rock is also incompressible? It's just assumption. This is the fundamental basis of the rest of the simulation courses that will follow through your entire program. So this is the most fundamental and basic way of teaching, and we would rather not to overcomplicate the system with no purpose, with no meaning there. So we start with this most simplest case, which is rock is incompressible, fluid is also incompressible. Next quarter, we have a dynamic modeling simulation course where we actually relax the two assumptions. Fluids can be compressible and rock porosity can change as well. So 1D incompressible flow, no source term. Imagine all I do is by boundary conditions, means that divergence velocity is 0. This is what we discussed last time. Or ddx in 1D of u would be 0. If there is no source term. If there is source term, it will be q. Now, let's study this problem with q alpha is 0. Let's just assume for this analysis. I have ddx of f times u. I can write ddx of f alpha u to be d dx of f alpha times u plus f alpha du dx. And I know this gentleman is 0. So I'm going to replace the hashed orange term with this orange term here. And to get that right, I'll end up with, instead of this equation, I will reach phi ds alpha dt plus u dfx becomes 0. This is only the analysis for 0 source term. Then I can rearrange everything and get to this way, that ds alpha dt plus u divided by porosity. Then I have df dx. With chain law, I can write it df ds ds dx is 0. So I have this multiplier and I have ds dx here. So see, this is change over x and over time of my conserved quantity, which is in this case S alpha. This is called wave speed or characteristic speed. This is the speed that if I wanted to relate it to wave equation, it would be the factor, this guy here. That would be the factor that would actually, if it's higher, it means change of the saturation would happen faster. If it is a slower, it would mean that change of saturation would go slower in a space. So this is actually, you see, this is in here, you have saturation over time. Here you have saturation over x. So the dimension of this is x over time. This is exactly speed. If you,
Sir,
go ahead.
is wave speed and characteristic speed, is that the same?
Okay. it is for this specific case, they are the same. It's actually characteristic speed has a meaning of derivative of the flux with respect to the conserved quantity. The way that I have reformulated everything, the two are actually the same.
Thank you.
Of course. If this is high, if this term is high, it means your saturation changes rapidly in your system. If it is a small, it means saturation would change very slowly in the system. The U here is clear for us. We understand U. If U is high, we know that it's going to be fast. But also not only U, porosity would matter. If porosity is small, then it has a small void volume. You've got small void volumes in your reservoir, which means that with the same velocity, you will transport saturation over time quite faster because it's smaller space to fill. And in here, if you have fractional flow functionality with respect to saturation, if the derivative of it is high, it means that also you will transport faster. So these two terms, F alpha with respect to S, gradient of this, and porosity here are actually coming because of your porous media system. If you didn't have porous media, porosity was 1, and you did not have any multi-phase effect of fractional flow, these two terms would just be going out of the system. You would mainly depend on only your velocity. Now, yes, I call this capital lambda because I need this factor. Go ahead. I had a question from someone. You're mute, I guess.
Ewald got locked out of the meeting and he tried to rejoin, but the meeting is locked. That's the message says.
Ask him to come back. I just unlocked the meeting. I don't know why it got locked. It just did automatically, I believe. So he should be able to be back. Please text him to be back. Thanks a lot for reminding me. Okay. This is characteristic speed. Now, knowing that this is an extremely important factor, and we need that for stability analysis as well. So knowing that, I'd like to now continue and solve my 1D transport equation that is written here. That's my transport equation. So let's work on that. Let me work on that. I'm going to now simply just delete this, and I'm going to take these just a little bit smaller, arrange it here. How nice for me to be able to do all these rearrangements here. Good. Now let's do what we did for flow. Is Ewald with us?
Yes, it worked.
Oh, fantastic. Sorry, it just got locked with no reason. I don't know why, but thank you. I'm glad you arrived. Let's assume I have a 1D reservoir, and I'm going to discretize it like I did before for flow. I am going to put my saturation unknowns at the cell center exactly where I put my pressure unknowns. So these are my saturation 0, saturation 1, all the way, perhaps saturation I minus 1, saturation I plus 1. And the system goes. Where would I put my velocities? Velocity was already set in the pressure solution part. Where did we put it? At the interfaces. Exactly. So this is where I have my velocities. This is velocity 0. This is velocity 1, velocity 2, all the way to velocity I plus 1, I minus 1. Yeah. So if I would get for cell I here, for cell I have neighbor I minus 1 on my left. I have neighbor I plus 1 on my right. And I have velocities at the interfaces here. This is a velocity in the left, and this is the velocity at the right boundary. UI plus 1 in Python ordering. So these are Python orderings. So in your code, you would do this way. So I put them in brackets that reminds you of, this would remind you of Python. Let's solve this problem then. The first term is phi. The first term is phi ds dt. Now, this is a new in discrete form because we worked with flow only with ddx. Now here I have ddt, which means over time. That's hyperbolic problem, by the way, right? This is a hyperbolic problem. Hyperbolic PDE, partial differential equation. Pressure, incompressible pressure, was elliptic. This is hyperbolic. And that's why we have speed of information. We have characteristic speed or wave speed. When I discretize it for cell I, and all with Python terminologies, obviously now, based on these terminologies here, based on Python based ordering, which means from 0 we count. Then I get phi s alpha for cell I at time n plus 1 minus s alpha at cell I at time n, divided by delta t, my time step, plus we have a divergence operator here. The divergence operator of a flux, we always said that with our staggered finite difference scheme, what we are going to do is that we are going to make it flux at the right interface minus flux at the left interface. So that would be F alpha at the right interface of between I and I plus 1. So how would I write it better, the best? I would write it F alpha at right interface between I and I plus 1. This is an interface between I and I plus 1. Would you prefer, I can write it at right interface of cell I as well. But I'm sure you know what I mean here. So this is the right neighbor of cell I. Right neighbor. Right I is the interface between I and I plus 1. What is U at the right interface with my Python ordering?
UI plus 1.
UI plus 1, fantastic. That is UI plus 1 based on my Python ordering. Minus F alpha at left neighbor of I times U at the left neighbor of cell I have what U? UI. divided by delta x. That becomes 0 or it becomes qi. If you have source term, you would write source term for phase alpha at cell I. If you don't have source term, you would write it 0. Now I can do everything here. I know what to do. The only thing that I don't know is what is my fractional flow at the right interface and left interface. How should I calculate the fractional flow function at the interfaces?
Mobilities?
So, what is, one more time, Barbara?
With the mobilities, I think.
Yes, but with mobilities, absolutely. We will do that with mobilities. The only problem is that mobilities are at the centers of the cell. So we need to do some sort of calculation to find how do we, let me just take it easy. I want to just simply make it a little bit smaller here so that we can just do better work with this. Okay, so that's what I have. Now my question is, what is F left and F right? So let's focus here. What is fractional flow? Is mobility's ratio. Absolute permeability would cancel from the fractional flow. So the fractional flow really is nothing else than, this is F alpha, which is lambda alpha divided by lambda alpha plus lambda beta. And if you write it for real multiphase flow, which you would learn in future in the course of physics of geosystems, this is KKR alpha over mu alpha divided by KKR alpha mu alpha plus KKR beta mu beta. Of course, I was sloppy here to put K inside lambda. I didn't want to make it two factors, but we know that K would cancel from this system, and it would actually mean that we are doing this. This is KR alpha mu alpha, KR alpha mu alpha plus KR beta mu beta. So this is exactly the definition of fractional flow, which is mobilities divided, and this is exactly what it is. And we will learn soon that this is purely a function of saturation. So it's a function of saturation that should be given to you as a function of saturation alpha. You can get it from experiments, from pore scale modeling, and these sorts of studies, bundle of tube theory, percolation theory, and stuff like that. And most of the times it would look like this in multiphase flow, like these sort of, it would look like this. So that's F alpha based on saturation alpha. That's this sort of function. Now, since I have developed my system for cell I have saturation I. This is cell I minus 1, and this is cell I plus 1. I want to know what should I use for fractional flow at these interfaces. What is fractional flow here between I and I plus 1? Fractional flow at the right neighbor of I, and here fractional flow at left neighbor I. Remember we had the same problem to find mobility, which in the flow problem, it was single phase flow, it was permeability. Here I want to know how should I estimate the phase property, not the rock. Rock doesn't exist. I want to know what should I put, because fractional flow is a function of saturation, and I have defined my saturations at the cell centers. So if I know saturation, I can calculate fractional flow. So for example, in the left neighbor here, I can calculate fractional flow with either with the saturation I, or with saturation I minus 1, or an average of it. What do you think I should use to calculate the fractional flow? With what saturation should I calculate it? Should I average it? Should I use I? Should I use I minus 1? What should I use for my F left?
Harmonic averaging.
We did that for flow because of permeability. Here, we are solving hyperbolic problem that has wave speed. For preservation of stability, what we do is we do upwind ski, which means we look at this characteristic speed here, which is lambda. So I see my lambda sign. If lambda is positive, it means the stream of information is from left to right, is positive. Then it means information is coming from left to right. Then if you are at the left interface, you calculate your fractional flow function using saturation of I minus 1. Use the left upwind. Upwind, because its information is coming to you. Use the saturation at the upwind direction to calculate your fractional flow. For F alpha at the right interface, use fractional flow at saturation I or I plus 1.
I plus 1.
I am at this interface and I want to know if I need to use I or I plus 1. And I see my characteristic speed says flow is coming from left to right. From left to right. And that's why for the left interface, I used I minus 1. So for the right interface, where is the information coming from?
I.
I, exactly. So I put I here. This is if, this is if lambda is positive, which means information is coming from left to right. If lambda was negative, you would do the other one. But the important factor here is that you use upwind direction to estimate your fractional flow functions here, these functions here. So I'm going to rewrite the equation above one more time. Finally, I say if my characteristic speed was positive, my saturation transport equation becomes phi S alpha I at n plus 1 minus S alpha at n I. Why am I writing it so big? I wouldn't get enough space for it. Let me just go, and also I can write it with blue. It becomes phi S alpha I n plus 1, which is time step n plus 1, and then it becomes time step n over delta t plus F alpha calculated at the right interface, so it should be based on S of I times U at interface I plus 1 minus F alpha calculated at saturation of I minus 1 times U at the left interface with Python ordering delta x is 0 or q. Or if you have source term, that would be q phase alpha in cell I. So that would be, because I can just clarify further, this is the velocity as well. With the Python ordering, we know that the right interface is interface number I+1. The left interface is interface I. And we know that because of upwind theory, for the left interface that is highlighted in green here, and I can show it with my pointer, the green interface, which is the left one, so I can make it green here for you, the left interface is going to be, the left interface is this one, for which we use saturation of I-1 to calculate the flux. And the pink interface would use saturation I, because lambda is positive. And that would be the Python-based ordering of what I would do. Now, I need to decide, because I have a time dependency, I need to decide what time step should we use to calculate F alpha. I know that I need F alpha at Si and Si minus 1. Should I use it based on Si and Si minus 1 of time step n or n plus 1? N or n plus 1? Which time step should I use? In this course, which is the introduction to simulation, we only use n, which is then explicit. We use explicit time integration scheme. Thus, F alpha will be calculated at time step saturation n of I, and F alpha at Si minus 1 will be at n also. That becomes explicit time integration. So I would calculate my fractional flow based on time step n, not n plus 1. Next course, we will do implicit. We will see how can we calculate it based on n plus 1. So if I use n, then this becomes n and this becomes n. Then I know everything. I know everything at time step n. I know everything at time step n. So I can calculate fluxes at time step n because I know the value. I don't know the value at n plus 1 at the next time step. I know velocity from the pressure part. From the pressure, velocity will be given to me, given from pressure, from velocity solver based on pressure, based from flow solver, given from flow solver. Grid sizes are also known to me. Saturation at time step n is known to me. Imagine I would also, since I would like to do explicit, I will also calculate if my source term is time dependent, if. I will calculate it also with explicit scheme. So this would be also known to me. So I would be able to easily find the saturation at n-1 because all the rest is known to me. Everything is known to me. My next step saturation, therefore, will be saturation at for phase alpha at time step n+1 for every cell I would be what? I need to multiply it with delta t, and phi would be equal delta t divided by porosity times qni minus delta t divided by porosity times delta x times F alpha calculated at saturation left interface based on upwind, so cell I U I plus 1 minus F alpha calculated at saturation of I minus 1 times U times U index I based on Python ordering. That is it. So I first can take the contribution of the source terms if I had any, then I will multiply this factor, then I have fractional flow times flux of right interface minus the left interface to obtain my main unknown, which is nothing but saturation at every grid cell I at time step n+1. Everything that I have here is at n. This is explicit method. This is explicit method. Now, I have one important question here. Can I take any delta t? Can I take any delta t and be able to solve this problem? Can I make my delta t 1 day, 10 days, 20 days, 100 days? Can I take it at any value that I would like to have? Remember last time, I would like to copy this formula here, in here, and keep it with me. But if I need it, I will just write it again, that's no problem. Remember last time we spoke about consistency and order of approximation. We said that consistency is when delta x and delta t, when they go to 0, your truncation error should also go to 0. And we only practiced that with x because we solved only pressure flow problem. So that was delta x goes to 0. That means that your error should go to 0. That was the consistency check. Order of approximation was how fast the error would go to 0. Would it be based on delta x square or delta x1? We found that the way we solved the pressure equation was second order accurate because of Taylor expansion. We found that. Now we would like to analyze our transport solver. If I discretize my transport equation, which is phi ds dt plus ddx of f alpha u is 0 or q, and I discretized it by writing it as Si n plus 1 over Si n plus 1. So I can just write it instead of Si. I can write it Si alpha. I have written it already up here, so I don't really need to really write it. I can just simply say this equation here has been solved this way. If I solve it the way that I wrote it already up there, am I going to be consistent? If so, what's the order of approximation? If we do the same Taylor expansion for homogeneous media, we will find that the order of approximation of this equation is with delta t1, which means it is first order accurate for time. Why? Because we approximated ddt of S as Sn plus 1 minus Sn over delta t. We just use the first order approximation of Taylor series. And this is extremely simple and convenient. That's why I don't really repeat it here. But imagine I can make Sn plus 1 to be Sn with Taylor series plus ds dt times delta t plus half of second derivative of s with respect to time delta t2 blah blah blah. I have only used this term and this term to approximate the derivative. So if I have rearranged the whole stuff, I will find that my Sn plus 1 minus Sn, so I bring Sn from the right-hand side to the left-hand side, becomes ds dt times delta t plus half of second derivative delta t2 and so on. And then when I divide both sides by delta t, I cancel this and I cancel 1 power. Then I see that that term here is an approximation of ds dt with error which depends on delta t to the power 1. That's why it is first order accurate. So that's why Sn plus 1 minus Sn over delta t is an approximation of ds dt with the order delta t errors. So if I refine my time steps by 2, my error would be twice accurate. For the flow, when I would refine my flow with delta x2, it would become 4 times more accurate because it was delta x to the power 2. Here is delta t to the power 1. So my time-dependent approximation is first order. But I am consistent, meaning that limit of my error will be 0 if delta t goes to 0. So I am consistent.
Sir,
Yes.
Edgar wanted to ask something, but his microphone doesn't work.
Oh, sure, please.
I think he said that you forgot the saturation from step n at the right-hand side at the equation a little bit more above.
Oh, right, of course. Oh, thanks a lot. Of course. So that becomes this plus SI. Thank you very much for letting me know. That would be this. that would be, oops, I can't. That would be, there is a minus saturation N here, which would go to the right-hand side and will be positive. So I'm going to, in fact, even do better, which means I put all of them here, and I would say this is S alpha N at I plus the rest. Thanks a lot for letting me know, Pele, about this. I absolutely forgot this.
Edgar was the one who saw it, so the credits go to him, I think.
What is it?
Edgar's the one who saw it, so the credits should have go to it.
Thanks a lot, but you should wave or do something that I could not.
I think my microphone is not working.
Yeah, but that's fine. But you speak with me and or put some papers in, or time out or something like this way that we bring doctors to them. Anyhow, but thanks a lot for being so sharp with us. That's absolutely right. As I should have been there. So this way of estimation is first order accurate. This is first order accurate in time. So consistent. But I have one more concern here. And the next one is, which is because it is a time-dependent problem, consistency, order of approximation, they are not enough. I need to know, is my discretization stable? Is it stable or not? What does stability mean? Stability means if you perturb the system by epsilon, would the error behave like avalanche? It would propagate, becomes bigger, and it would crash your system? Or it would get damped and it would go back to its original stable form. For example, this system is at this state, the ball is stable. But if you perturb the ball a little bit, it would fall, right? You wouldn't do this way of simulation because you always have approximations in your computers. You always are perturbing your system. So this, although it looks like to be in the stable mode, a little bit of perturbation would not make it to stay where it is. But this system is stable. You perturb the ball a bit left or right, it would come back to its original position. So this is unconditionally stable. This is not stable. How about this one? How about this one? So imagine the ball is the blue one. Is this stable? As much as you do not perturb it too much, yes, it is. But if you perturb it too much, it will be unstable, right? So you have a limit for your stability in this system. So we call it conditionally stable. Now, stability comes with error propagation over time. And that's why we did not study that for flow, incompressible flow, because it was elliptic. There was no time there. Here, we have time dependency. My question is this: can I take any delta t? Can I take any delta t and remain stable? Can I take any delta t and remain stable with this formula? Since I used explicit method, so I estimated my fluxes at time step n. So I used time step n to estimate my flux. We can do von Neumann linear analysis and prove that your delta t should be always smaller than delta x divided by your characteristic speed in order to remain stable. Which means delta t multiplied by your characteristic speed divided by your delta x should be always less than 1. Which means you can write it as a CFL factor times 1, which is times 1 would be. So CFL times 1, where you impose the CFL factor to be less than 1. If you multiply this factor and enforce that this factor is called CFL, that your factor CFL is always less than 1, then it means that your delta t, is less than delta x lambda. Or you can say, let me take my delta t to be equal to CFL times delta x divided by lambda, and enforce that my CFL is always less than 1. If you take delta t smaller than delta x over characteristic speed, you will be stable. However, if you take it for bigger delta t's than this value, you will crash. A small error would increase over time. CFL actually is the first letter of the 3 scientists who developed this: Courant, Friedrich, Ludwig, or some. So it's actually, there are names there. So it's CFL. So imagine Pele, Barbara, Beer, Ewald would do that. They would call it EB, I don't know, P, and so on. So just try to find your own conditions for, I don't know, a simulation coolness factor. Then you develop your own factor. Yeah. So CFL is actually the first letter of those fluid mechanics people. So delta t should be smaller than delta x over lambda. And that is the condition which would enforce the factor here, CFL, be less than 1. Then you are stable. That's why explicit schemes, whenever they are used, you would use them for small delta t's, because you cannot take large delta t with them, because you would crash. Your error would propagate in time. As the last story to discuss in the class, I would like to actually do that here. I couldn't prepare before, because usually I do that for the pressure compressible part, but that's fine. We will try right now to see if we can prove this, that our error would propagate over time if delta t is more than delta x over lambda. So I'm going to do a little bit of math without much preparation, which is fine. But let's see if we can prove this. And then we would be done with our transport lecture. Okay. So what I'm going to do is I'm going to pause, stop screen sharing, and then pause Zoom recording. Okay, now I'm going to do some sort of analysis to prove for you that you cannot take any delta t for your simulator that you're going to develop this Friday, because your system would no more be stable. So I have, in the break that you had, I was working here. So I wrote again the transport equation with 0 source term. And since it's incompressible flow with no source term, then divergence or ddx of u is 0. And therefore I brought u out of this ddx because its divergence is 0. And then I put porosity, which was here in the denominator. I brought it down there, This is velocity, and I wrote df dx to be df ds, ds dx. We have done this practice already before in this class. And I called the whole term here u over phi df ds as capital lambda, Greek lambda, which is characteristic speed or wave speed here. And I've got this here with us. So that would be the equation that I have. If characteristic speed is positive, I can discretize it with this, with the first term wouldn't change much. I mean, wouldn't change at all. Then I have this lambda here. Then because in the right and left interface, in the right interface, I'm going to use saturation I. And on the left interface, I'm going to use saturation I minus 1 because of upwind values. Then this would be my discrete equation. So I have used explicit and upwind values to discretize that. I would like now to do some linear stability analysis. Linear stability analysis, which is valid for linear systems. That's why we say linear. If the system is linear, we can do some stability analysis by pen and paper. And von Neumann did that study as we call it von Neumann linear stability analysis. If you want to know the precise name, so it is called actually von Neumann linear stability analysis. Yeah. Okay. That's the linear stability analysis. So this is the whole story is based on one simple thing that you need to get it right. Let's define what is the error. Let us define what the error is. The error at point I and time step n is the difference between exact saturation at time step n. So I would just call it bar n with the saturation value that your simulator would give. That's the error, right? SIN is the exact solution. SIN is your simulator numerical solution. Now I would like to do something nice here. What is the error? If I find my error over, let's say, a space, it will have some functionalities, right? And the value of this would be a time-dependent problem. So that is the error for time 1. For the next time, maybe it becomes more or less, or it may become different. So it has time dependency and spatial dependency. With Fourier analysis, with Fourier expansions, series expansion, I can write any continuous function as error, which is a function of space and time, as over a space, I am going to expand it with frequencies of different frequencies. So error has different frequencies, which would be superposition of some time-dependent value with some frequency IKMX. IKMX is cosine and sine, which is frequency, which is the oscillatory part. And with this value, with this weight, I can cluster them all and find what is my error at this time. At the given time, it will have a magnitude, amplitude, and it will have sequences of frequencies with it. For the error at n and cell I, my error, one of the modes would look like AT times e to the power minus kmx. That's one of the modes. I take one of the modes with me, and not all modes, not all of them. So I would like to only take one of the modes with me, okay? And here I am going to have summation over m from 1 to number of frequencies that I have, but I would like to only focus on error mode m for one of the frequencies. If I prove that one of the error frequencies, the magnitude of it, amplitude of it, is going to be damped, then generically I have solved it. M can be 1, 2, 3, 4, or capital M. I want the mth mode of my error to damp over time. That's my purpose. If this is my error at I, if this is my error at I and time n, my error at I at n plus 1 would be simply e to the power t plus delta t. My time is delta t forward because it's n plus 1, but it is at the same location I. So it will be still minus I kmx, which can be written as e to the power a delta t times error I n, because that is still at and minus this. This is exactly at and this. So there is only extra term here is the delta t times a. My error, what other error do I need? My error at I minus 1, because I have saturation I minus 1 here, and at time n. So at time n and at location I minus 1 will be the same time, but location is minus 1. So it will be minus I km, but x will be x minus delta x. This will be, I am going to factorize what is the already error of in. I have this and I have this factor already here. So I can write it as e to the power I km delta x times the error at n. So if error at I is given to me like this, error at I and time step n, the error at I and time n plus 1 has a proportionality with that error n, and error at time n, but location I minus 1 would be proportional with the error of in like this. Now, what happens if I use this formula to see what would be my error? If I use my formula and say, this is the real Si plus 1, and I know that my simulator Si plus 1, which is S, this is my simulator saturation is the error and the exact solution difference is the difference between the error and the exact saturation, which means that Si, let me just take this, This means that I am going to make this to look very small and then delete this. And then what else would I like to have? It is a stability. This means that my simulator saturation is, with this definition, would be the exact saturation minus error. And I can now substitute this relationship with every single term that I have in my governing equation, which would mean that I would go for Si at n plus 1 will be Si exact n plus 1 minus the error I exact error, error at n plus 1 minus Si exact at n minus the error at n divided by delta t plus lambda Si exact n minus error at n minus Si exact minus 1 minus error at I minus 1 n divided by delta x is 0. I replaced every saturation with the exact saturation minus the error. These are exact saturations. And the orange ones are the error terms. I know the exact saturation satisfies this mathematical equation precisely. So I know exact solution divided by delta t will be equal to this, because exact solution does not have any error. Now I will get a formulation for my error. I can multiply everything by a negative sign without any difference. So I find that my error at n plus 1 minus error I n over delta t plus gamma over delta x times error I n minus error I minus 1 n is 0. This is the formulation that my error now has, which actually is great. Why? Because it tells me how my error at next time step depends on the error at time step n. This is where I need to do mathematical analysis to make the error at n plus 1 become always smaller than the error at time step n. Then I become stable. Now I can say that my error at time step n plus 1 is, I put everything to the left-hand side, to the right-hand side, will be error at n plus delta t over delta x gamma times epsilon I minus 1n minus epsilon I n. I made it negative because when I bring this to the right-hand side, it will be minus of that term. So that becomes minus. You could keep it the same. You could keep it to be I and I minus 1, I and I minus 1, but then you need to do this to be minus. So I put everything to the right-hand side term and then multiply them with delta t as well. Now I am going to use my error relationships. I know that my error at I is given to me. I know that my error at I minus 1 is what? My error at I minus 1 with these Fourier analysis for the mth mode is nothing than just e to the power I km delta x times error I n. That's for the mth mode, not all of them. Okay. So this means my error at n plus 1 is error I at n times 1 minus delta t over delta x lambda. I am factorizing epsilon I from every term. This term would give me 1. This term, its epsilon would go away. So I get this in here. Then it would be multiplied by 1 minus e to the power I km delta x. That will be the formula that I'm going to have at the end of the day. And no, I want a stable simulation. What does a stability mean? It means my error at n plus 1 divided by the error at n, norm of it should be smaller than 1, right? Which means that the error at n plus 1 should be smaller than error at n, isn't it? That's the meaning of a stability, that error would decrease over time. I can call it like g at I. So this means if I do that using the above formula, I have E here, I have E here. So I bring this to the left-hand side. I get epsilon at n plus 1 divided by n will be 1 minus delta t over delta x lambda times 1 minus e km delta x. When I want, by the way, we could also learn what that is. What is EIN plus 1 divided by EIN? What is EI plus 1 here? Is error I times e to the power a delta t. That's this. So I can actually come here and say that is e to the power a delta t EIN over EIN, which is e to the power at, which is actually the magnitude. Frequency is the same, it's only the magnitude. This is just a side note to let you know when we want this to be less than 1, it means I want the magnitude, the amplitude of my, I'm sorry, this is not t, this is delta t. This is delta t. I want my amplitude over time decrease. That's the other meaning of it. So over here also, this is the magnitude of it should decrease over time. So I want my error for cell I at n plus 1 divided by my error at cell I for n to be less than 1. So I want, in another way, 1 minus delta t divided by delta x lambda 1 minus e I km delta x be smaller than 1. That's what I want, because this is exactly the formula that I got up in here. And I want my error ratio to be smaller than 1, to be smaller than 1. This function here is sinus and cosine. So it's cosine and sinus. It's always between 0 and 1. 1 minus 0 is 1. 1 minus 1 is 0. So this function here will be between 0 and 1. It's between 0 and 1. This is also 1. So what can I say for this factor if I want the entire factor to be smaller than 1 all the time? This factor will be smaller than 1 when delta t times lambda over delta x is less than 1. Which means that I proved to you that your delta t should be smaller than delta x divided by lambda, and I can be feeling well that I remember mathematics from my kindergarten. That was actually one of the exam questions of my qualification exam at ETH. So that's why I never forget this mathematics, because I had to do that orally. This is exactly the condition for stability of time step that I have, and explicit schemes are stable if your delta t is smaller than delta x over characteristic speed. If your characteristic speed is very high, so information is traveling very fast, you need a small delta t to make it stable. If your lambda, your characteristic speed, is very slow, information is traveling slowly. Therefore, you would be able to take larger delta t, relatively, bigger delta t. This is CFL condition. Now we are done with the theory. What we are not done with is now going with the code and start to go through the entire lecture one more time and program with Python what we did. Then we can say we learn it. Because when you do this and implement it and you check with small delta t, you will converge. If you don't use this delta t, you use bigger delta t's, you will be unstable. Now, let me be back to this part. Remember I said to you about consistency, order of approximation, and stability. If my numerical method is consistent and it is stable, if this and this, then I can say my numerical method is convergent. Convergent schemes are consistent and stable, which means their error, delta t and delta x, the error will go to 0 if delta t and delta x go to 0, and the error does not propagate over time. So you will stay convergent all the time. You are consistent and you are stable. That's the meaning of convergence. You converge to a solution with them. And since we did explicit scheme, we have a CFL criterion to satisfy. Now, how do we do with multidimensional? If I find my slides, how do we do with multidimensional? Precisely the same. Precisely the same as the one-dimensional. This is also in your practical. You are going to go through this as well. So if you want to do, let me go to the presentation mode and see what screen should I share with you. So I believe that this would be the right thing to share. Do you see my two-dimensional slide?
Yes.
So see, this is exactly the df dx, flux is at x, and then you have the dy of flux as well here. And there you can just simply say, I don't have only west and east, but north and south. So you would calculate your characteristic speed, which has a velocity in it, and porosity and fractional flow derivative at each interface. Then you decide what is the upwind direction for each interface. And based on the upwind direction at each interface, you would discretize your equation between I and I east, I and I west, I and I north, I and I south, and then find your fluxes. We are going to practice that in the practical session. Science is the same. We are going to just do 2 times the same stuff that we did here. So if for example, at the interface between I and I east, if characteristic speed is positive, you use the property of I. If the characteristic speed was negative, you would use the property at I east. Same would hold for the other one, for I and I west. And for the north and south, you would do exactly the same. If your characteristic speed at the interface between I and I north was positive, it means the flow is going upward. Then you would use the fractional flow to calculate your properties, fractional flow at this interface using property of I, saturation of I. If characteristic speed was negative, and then you would use the I north, because negative means it comes from top to bottom. One last question. To calculate characteristic speed at every cross section means that you need to go to characteristic speed calculation, which is given here. Velocity is given to you. You need to calculate you need to find out what's the value of derivative of fractional flow. What would be the derivative of fractional flow at this interface? Would you use saturation I or saturation I north? Which one would you use? To calculate your lambda at this interface, to calculate your characteristic speed, you need to find the derivative of fractional flow value. Which saturation would you use to find the DFDS? I or I north for that interface? Remember, you want to do that to calculate what is your characteristic speed, so you don't even know your upwind direction at that stage. You will know your upwind direction based on the sign of lambda. So you don't know anything yet. You want to start the simulation. You want to find out what the lambda is. So you need to calculate your lambda at that interface. How would you do that? We do an averaging most of the time. If saturation here and saturation here we know from n, we take an average and calculate the lambda. Now remember one thing, lambda, the value itself is not crucially important. We need the sign of the lambda to see if the flow is from top to bottom or bottom to top. So if lambda calculated based on saturation I and lambda calculated based on saturation IN would have the same sign, you wouldn't be affected much, except the fact that your time step size needs the exact value of lambda, but then you will be a little bit approximate, fine, you go for the most conservative lambda anyhow. So you take the delta t for which everybody is happy and will be stable, because lambda changes across different interfaces anyhow. The problem will happen when lambda is positive based on saturation of north, and it will be positive based on saturation of south or n, or it will be negative, positive differently. Both would be, one would be positive, the other one would be negative, like this, positive, negative in one interface, or both would, the left one would be negative, the right one would be positive, which means like this. There are 2 points, 2 problems. One is you go this way, another is they go this way. So the sign of lambda would be different if you would calculate based on I or I plus 1, for example. These are complex situations that happen when you have gravity and capillary pressure in your system. That's why simulators have difficulties to simulate the complex physical problems. When waves merge, you have the formation of shocks. When they depart from each other, you have sonic points. There was an impactful mathematician, Godunov, who actually studied these rigorously. And we have Godunov schemes and higher order methods, SVD, TVD, total vanishing, total variation diminishing, TVD schemes for higher order. There is a vast literature and still is an ongoing research how to stably simulate complex problems when lambda or characteristic speed changes its sign in one interface. What is really happening? You are not going to observe these complexities, unfortunately, for your two-phase flow system. In real life, you may encounter problems, but these are, for many of them, we know the solution of, by the way. But I wanted just to let you know about that. But all of them you're going to practice in your practical session. There are higher order methods, so you don't really have to go only one cell property to calculate. You can go to more cells. I leave it out for this course. One advice I have for you is please, if you get time in future, read this textbook, Numerical Methods for Conservation Laws by Randall Levesque. It's a beautiful textbook, and I've read it multiple times. It was part of my exam when I was a kid as well. So that was half of our course. It's ETH lecture notes, by the way. So this is the time he actually was giving the lecture there. And it's just so nice, so comprehensive. And in the case you in future face to some difficulties with hyperbolic type of problems, transport problems for simulation, and I was not accessible at that time, please refer to this textbook. Most probably you're gonna find your answer. It's also a very thin book, about maybe 80 pages or so, but it's so comprehensive and nice. So with that, I'd like to thank you all for being with us for the transport part of the equation.